Lesson 6.5, Indirect Proof and Inequalities in One Triangle. Let's talk about indirect reasoning. Imagine you're taking a multiple choice test, but you don't know the correct answer. Does that sound familiar? However, you know some answers are incorrect. So you eliminate those answers. So instead of A, B, C, D as your options, you know it's not A, you know it's not C, you're pretty sure it's not D. Oh, that leaves B as your correct answer, because it's the only one that's left. That is indirect reasoning. You don't really know the answer, but you eliminate all the other possibilities. That same kind of logic can be used to prove geometric things and theorems and so on. Eliminate all the other possibilities, so whatever is left must be the answer. So indirect proof is proving things by making an assumption and showing that the assumption leads to a contradiction. Essentially, indirect proof is proving things by eliminating all the other possibilities. So whatever is left must be the correct answer. So how do we write indirect proofs? Well, you start by identifying what it is you're trying to prove. So you're trying to prove these are congruent. Temporarily assume the conclusion is false and that the opposite is true. So what you would assume then, if you're trying to prove things are congruent, is you do the opposite. They're not congruent. So whatever it is you're trying to prove, you assume the opposite is true. Then you show that that assumption leads to some contradiction. It can contradict the hypothesis or some other known fact in geometry, but the assumption that what you're trying to prove is wrong always should lead to a contradiction. Then you point out your assumption must be false since it leads to a contradiction, and so the only thing left, the thing you're trying to prove, must be true. Suppose you wanted to prove the statement, if x plus y does not equal 14 and y equals 5, then x does not equal 9. What temporary assumption could you make to prove the conclusion indirectly? Well, we're going to take what we're trying to prove and do the opposite. This bit, x does not equal 9, is what we're trying to prove. So we're going to assume the opposite. Assume x does equal 9. See, there's a difference there. Does equal instead of doesn't equal. And then we run through our little proof. All right, so if x equals 9, then if we have x plus y doesn't equal 14, and y equals 5, we could plug those in. So I'll have 9 plus 5 doesn't equal 14. So 14 doesn't equal 14. This is a contradiction since 14 does equal 14. So our assumption is wrong and x cannot equal 9. Well, technically for this question we just wanted that part, but you know, might as well go ahead and do the whole proof, right? Let's try another one. Write an indirect proof that if two lines are not parallel, then the consecutive interior angles are not supplementary. So we're given the lines are not parallel. We're going to prove those angles are not supplementary. All right, so we're going to prove the angles are not supplementary. So we're going to assume the opposite. So we're going to start by assume angle 3 and angle 5 are supplementary. So we're doing the opposite here. And then what? Well, if they are supplementary, what do we know? Well, if they are supplementary, we know then that lines are parallel. So then line L would be parallel to line K by, well, what kind of angles are those? Those are consecutive interior angles converse. If the consecutive interior angles are supplementary, then the lines are parallel. Well, what's the problem? Well, this contradicts the given. So, the assumption is wrong. And angle 3 and angle 5 are not supplementary. We eliminated the other option, that they were supplementary, showed that that was wrong, thus the only remaining option, they're not supplementary, must be true. All right, let's learn some theorems. So we're going to start by drawing a scaling triangle, and we're going to measure all the sides. I'm going to use centimeters as seen on my iPad. So I have the bottom is 9.7 centimeters. So hypotenuse looking one is 10.3 centimeters. And this one is 3.7 centimeters, or close to that. All right, also measure the angles. Well, this one, as you might have guessed, is 90 degrees. The small one is 22 degrees. And so the other one should be 68 degrees, because they all have to add up to 180. All right, what do we notice? I don't know. What do we notice? The smallest side. So our smallest side here is opposite. Oh, what do you notice about that angle? It's opposite the smallest angle. And the largest angle, that one, is opposite the longest side. So the small side is opposite the small angle, the large side is opposite the large angle. How interesting. That is our theorem. So our first theorem is the big angle opposite the big side theorem. Now I made up that name. It's not the one from the textbook, but it's one I like. It says if one side of a triangle is longer than another side, then the angle opposite the longer side is larger than the angle opposite the shorter side. If we like, the biggest angle is opposite the biggest side. You could expand that to say the smallest angle is opposite the smallest side. The converse is also true. The big side is opposite the big angle. If one angle of a triangle is larger than another angle, then the side opposite the larger angle is longer than the side opposite the smaller angle. The big side is opposite the big angle. Small side is opposite the small angle. So here's angles. Let's list the sides in order from shortest. If I want the shortest, I'm going to start with the smallest angle. So there's my smallest angle. So that is the smallest side. So the shortest one is ST. And then the next one, the middle one, I'm going to call it the medium one, is there. That's RS. And then the longest, which we could tell from the picture. Not that you can always tell things from the picture, but longest one is RT. Smallest sides opposite the smallest angle, biggest sides opposite the biggest angle. All right, one more theorem. All right, draw a triangle with sides 5, 2, and 2. All right, well, there's a 5. Okay, and here's a 2, and there's a 2. So what's the matter with this triangle? Oh, it doesn't make a triangle. The sides don't touch. Well, let's draw a triangle with sides lengths 5, 2, and 3. There's my 5. Here's my 2. And here's my 3. All right, they almost touch. They don't quite touch. If you look at the lengths, the only way to get the 2 and the 3 to make 5 is if they're a straight line. So it forms a line, not a triangle. How about 5, 3, and 3? Well, there's the 5. Here's one side that's 3. Here's, yeah, I didn't do this great, but there's another side that's 3. But anyway, you see it makes a triangle. So what do you notice? Well, when these two short sides don't add up to make the biggest side, you don't get a triangle. The only way you get a triangle is when the two shorter sides are bigger than the third side. That's the triangle inequality theorem. The sum of two sides of a triangle is greater than the length of the third side. So you add two sides of a triangle has to be bigger than the third side. In reality, if you add the biggest side to anything else, it of course will be bigger. So the two smallest sides have to be greater than the longest side in order to get a triangle. So the two smallest sides need to be greater than the longest side. A triangle has one side of 11 inches and another of 15 inches. Describe the possible lengths of the third side. Well, let's see. We want the two smallest needs to be greater than the longest. And our sides are 11 and 15 and call it x. So if the 15 is the longest, I'd have x plus 11 is greater than 15. If 15 is longest. Subtract 11, so x would be greater than 4. But what if 15 is not the longest? What if x is the longest? Then it would have to add the 11 and 15, and that would have to be greater than x if x was the longest. So that would be 26 is greater than x. All right, so we're going to put this together. X is bigger than 4 and smaller than 26. So you'd write it like this. X is between 4 and 26 inches.